Okay, good evening, everyone. Please
Please can
confirm.
you
Yeah, confirm that you can hear me.
hear me?
Okay, Bill, can you hear
We
me?
can hear you.
Okay, good, good. Thank you so much. I will just go
We
ahead
can
and
hear
share my
you.
screen. Yeah, I'll just go ahead and share my screen. So let me know when you can see my screen. Okay, can you see my screen now?
I can see your screen.
Okay,
Yes.
so thank you so much. So thank you, Bill, for that overview. And I believe that over our course of learnings in the past months now has always revolved around the basics. And we are intentionally doing that because we want to build knowledge upon knowledge. So we want to set the foundation right because as we are moving forward, we are going to encounter some advanced topics in petroleum engineering. So we want to make sure that our foundation is very solid so that when we are talking about those advanced topics, it won't be like we are trying to complicate things. We will now be relying on our foundational concepts. So, as Bio has said, we have done some things in the past, and here is another one: introduction to sampling and PVT properties. So, I will be taking it this way. First, we start with a little bit an overview of PVT analysis. We have like an introduction of what this PVT analysis is, the relevance and various applications in our industry, especially when we want to streamline it down to our petroleum engineering domain. Then the second one would be a review of key PVT parameters. So the time we come hereby, I will just mention some PVT parameters, if possible, explain them, and we equally look at sources of PVT parameters. Yeah, we look at sources of PVT parameters, and we know that we have maybe three types or three sources: the laboratory, the black oil correlations, and the compositional analysis method. That's the equation of states. We are going to equally look into that. But some of these things are things that have been structured. So even if we may not cover them now, subsequently we are going to cover them. Then part of our practical case study will be where we are going to be looking at a typical PVT report. And I know that majority of our universities, we don't usually talk about PVT reports. So when you see a typical PVT report, you don't even know where to start from. You are seeing ROS values at different pressure points. You are looking at maybe your BO, BG, all of these values are different pressure points, and you don't even know how to start or where to start from and the particular PVT parameter you are interested in. So these are some of the things we'll be doing during our hands-on session. Okay, so let me start by doing this. Let me go ahead and get my pointer. Okay, so if we can still remember our chapter one in Tarek Ahmed that talked about the uh, fundamentals of uh, reservoir fluid behavior, we can remember that there is something called the phase envelope, okay, which we usually call the
Oh,
pressure
Matt Wheeler.
temperature diagram. Yeah, so please, you can mute if you are not talking. Okay, so we usually have this, which is pressure, temperature, and the whole idea of this is that we use it to describe because we have observed over time through some
Oh,
studies that, Bio, you are not muted. So through some studies that our reservoir fluid tend to behave in certain uh, unique ways whenever they are passing through different um, pressure and temperature values. Okay, so they tend to behave in some unique levels. So that's why we use the pressure temperature diagram to analyze them and equally classify our various fluid oil types. So The typical one I'm using now is the ordinary black oil, and we know that we have the black oil, we have the volatile oil, we have the retrograde or the condensate, we have the wet, and we have the dry gas, right? So each of them have their own unique phase envelopes. So it's something that you will like to read up. So first things first, let's start with a little bit definition of our hydrocarbon system. So when we define our hydrocarbon system or hydrocarbon, we usually define them as a complex mixture of organic compounds in the faces of some other impurities, right? So majority of the things we work with is a combination of hydrogen and carbon, and these mixtures are usually complex because you will have some components of those crude oil samples, the C7 plus, and some other higher C numbers. Okay, so they are complex. Those C7 plus, they have some complex behaviors around them, and one of the rule of a good petroleum engineer is to be able to study the behavior first of the crude oil sample he or she is working with, and able to categorize them so as to determine how every other plan, starting from reservoir management down to production and down to uh, the flow lines, down to our access points, everything ranging from this is something a petroleum engineer needs to be fully aware of. And all of these things, from the reservoir down to the well, down to the flow lines, down to the set point, they are all of them are a function of PVT parameters. Okay, so let's now go ahead and study this sample and look at what we have here. So in our first envelope, right, we usually have this to be the bubble point line. Okay, so then I won't really explain this like the classroom. That's why we have our textbooks, right? So you just go ahead and read them up. So we have this bubble point line that separates the liquid phase, purely liquid phase, and the mixture phase. Then we have the dew point curve. This separates the gaseous phase from the two phase, right? Then within this two phase, that's where we have a composition of the liquid and the gaseous, right? So this bubble point line actually informs us, gives us clue of our saturation point, right? So if you observe, looking at this ordinary black oil now, you observe that at the reservoir pressure, at this initial reservoir pressure, is purely within the liquid phase. So this ordinary black oil at the initial reservoir condition is purely liquid, right? It doesn't have any gaseous component of it. It's a single phase. But as soon as the pressure was dropping down to the bubble point line, you notice that some fraction of the gaseous phase, as soon as we move a little bit down from there, taking note of the critical gas saturation, we are now having 9 liquid and 10% gas. Then as we proceed down, we over here we are having 80% liquid and 20% gas. And you know that the higher the pressure, the more gas will be dominant within the oil. So as you reduce the pressure, there will be some spaces for gas to expand. Okay, so and this wet part or this part now you are seeing is actually capturing what happens as we produce our oil from that high reservoir condition down to the surface where we have lower operating conditions. So this alone has passed the message that our crude oil sample, the state and the characteristics it has at reservoir pressure is not and may not be the same when you take it to the surface unless your pressure and your temperature are kept constant. That's something to note. So with this alone, a good understanding of PVT. So in essence, this the whole takeaway you can make from here is that your PVT understanding is what will help you to understand the dynamics of your crude oil sample, how it rotates, how it behaves. So the more understanding or more grasp you have about PVT, the more you can effectively manage your resources. That's why in the classroom they will just teach you this, give you some definitions, but when you come into the industry, you see yourself using this knowledge, using these concepts very well. So moving forward, what are like the relevance and applications of PVT analysis? First of all, in reserve estimation. So one of the things we do around, like one of the jobs of a reservoir engineer. Okay, a reservoir engineer, a typical reservoir engineer has three major tasks or job roles. One is that he estimates the oil in place, right? He estimates the oil in place. Then he equally informs us of the ultimate recovery, which is a function of the recovery factor. Then he attaches a timeline to that ultimate recovery. So when we say oil in place, we are talking about the total volume that is in our reservoir, right? The total volume of oil that is in our reservoir. But we know by physics and understanding of physics that we can't recover all those the complete volume. So we need to equally ascertain before we can make our investment, we need to ascertain the volume, the fraction of this volume that we can extract from the reservoir, right? That fraction we can extract is what we call our recovery is a function of our recovery factor, right? Then when we now use that recovery factor, which is usually a fraction, and multiply that STOIP, that's the stored oil in place. This one has been expressed in surface condition. But when we now use that recovery factor to multiply that our oil in place, we are now sure that this is the volume that we can recover based on our constraints from that reservoir. But additional job of a reservoir engineer is to attach a time scale. So he equally forecasts and tells us that this volume of this recoverable volume, we can actually produce it completely or to some economic limit within 50 years interval or within 60 years interval. Okay, but what makes it possible for a reservoir engineer to complete his job by estimating the oil in place is that he needs a PVT parameter. And what's that PVT parameter? That is our BO. That's the oil formation volume factor, right? This is the factor that converts the oil volume from the reservoir down to the surface condition, right? Now imagine a case whereby a reservoir engineer must have estimated the oil in place at stock tank condition with a wrong formation volume factor. He will now run into a problem. What's that problem? He can either overestimate, and when he overestimates, obviously there will be more investment in that project with less return. Then when he underestimates, there will be less amount of investment and something that has a good potential of providing money for us in the industry, we end up losing it. That's why good PVT uh, data, quality PVT data is necessary. Okay, another thing is there's something called material balance equation and material balance modeling. This is just typically trying to uh, model our reservoir as a kind of tank. So when we model it, we use it, carry out some regression analysis around it, and we can use it to make some estimates, revalidate, and equally make some forecasting too. So uh, in that in that type as well, we make use of, if you see a typical material balance equation, you will always see things around, you see some BO, RS, ROP, all those things are reservoir, especially RS, BO, BG, all those things are PVT parameters as well. So another one that is key is underflow assurance, right? We want to make sure that if we are transporting, let's say 20 barrels of oil from one point to another point within our flow line, we must make sure that we carry out that exact quantity right? Transport it from one place to another. We must achieve that. But we know that a point change from point A to point B will invariably result to something like a pressure drop. There will be change in pressure, which will now make our fluid to change, right? So flow assurance is just trying to make sure that the amount or the volume we want to transport is actually what we are transporting. So that flow assurance is dependent on our PVT parameter. So we want to know, we need to understand the tolerable operating conditions in terms of pressure of that our crude that we want to transport, such that we need to maintain our flow lines, make possible settings and adjustments to meet up to that standard, such that as we are making that transportation of our fluid or passing that our fluid from one point to the other, what we actually trying to achieve, we achieve it. That's the whole idea of this flow assurance. That's where another place where PVT plays key role. Then in our wellbore hydraulics, yeah, this is another important area, right? So when we do inflow, when we do things around inflow analysis, we are just trying to understand what rate will our fluid from the reservoir flow our into our wellbore, right? And our wellbore over here we are talking about is just somewhere around here. So when we are doing inflow analysis, we are just trying to know how much of this volume within the reservoir and at what rate can enter into this wellbore. Then when we are looking at outflow analysis, we want to know at what amount of this volume that entered can actually come out to the surface. So we need those two things to happen for us to maximize value, right? So, and in those studies, in either of those studies, we actually need PVT parameter too. So you will see things around trying to reduce pressure drops, trying to reduce pressure drop due to friction, acceleration, elevation, all those things. When you actually discretize them and find their root formula, you discover that the equations used in estimating each of these pressure drops, you have various PVT parameters attached to them. So any mistake or any compromise in any of those PVT parameters, you end up coming up with a wrong well modeling or a wrong well model that will inform wrongly the decision that is being made around that asset. Okay, there are equally some other areas cutting across different areas, even in drilling. You know, in drilling, we want to avoid lost circulation, we equally want to avoid kick, and all those things are a function of the reservoir, the pore pressure. And that pore pressure we are talking about is a combination of the fluid pressure and the rock pressure as well. So the fluid pressure, if we are talking about the fluid pressure, we are equally talking about looking at the density of that fluid, which is equally PVT parameter as well. So it cuts across any area at all in the whole of the upstream sector as well as the other sectors. All right. So let's move further. Let's move further now. Um, there are different classifications that can be given to PVT analysis. Okay, there are different classifications of PVT analysis. So generally, we can classify them into three. We have the volumetric property method, and we have the transport property, then we have the thermodynamics. Okay, so in the volumetric property, we are trying to look at those properties that describe the volume of the fluid changes in response to variations in pressure and temperature, right? So uh, we are looking at things around density, gas oil ratio, oil formation factor, gas formation factor, condensate gas ratio. So we are looking at all these things as things we know that these are the properties, the PVT properties that respond to volumetric changes, right? So these are PVT parameters that we can call or explain to be volumetric. Okay, then we have those ones that those PVT parameters that actually control or influence our transport system. That's where you will talk about the viscosity, which the ease of flow. Then you talk about thermal conductivity, right? Then you talk about diffusion coefficient. Then around thermodynamics, where we are looking at heat and heat change, right? Heat motion change. You are talking about enthalpy, entropy, the specific heat capacity. I think these are the ones we did back then in physics. Then you talk about the Joule-Thomson effect, things around these areas as well. So all these things are various classifications of PVT parameters, which will be very helpful to us whenever we are making some kind of studies. Okay, so when we still progress, these are some of the things that we'll be calling back, we'll be regressing back to these various properties, and that's when you will see some more explanations about them. So at this point, I will be summarizing our presentation or our discussion around these PVT sampling methods, because it's something that is very key for us to understand. And when we understand it very well, there's a little quiz in the next slide which we are going to answer together. Okay, and that quiz will actually help us to appreciate each of these PVT parameters with respect to the sampling methods that we want to employ. So we have two major types. Okay, we have two major types of PVT sampling. And when we say PVT sampling, what are we actually referring? We're actually referring getting those samples. Okay, getting those samples. We want to get these samples from the reservoir, or we want to anyway, we just want to get the sample, and that sample must be a good representative of that reservoir that we want to study. Okay, so there are two methods. We have the downhole sampling and the surface sampling, right? So in the downhole sampling, before I come to that, let me talk about wellhead sampling. So in the surface sampling, is kind of divided into two, but we just categorize them as surface because we have left the well and we have left the reservoir. Okay, so in surface sampling, some persons will further divide it into two. They call it the wellhead sampling, which is the case we have here, or separator sampling. Okay, so in the wellhead, they want to pick the information at the wellhead, so they will need to work on some valves and get fluid without actually going to the separator to do the collection. While the separator sampling is when you want to go to the separator, already the separator has done its job of actually separating it into gas and the oil. Okay, so you want to get some samples of gas, get some sample of oil, and do what is called recombination. So you recombine them together to have the same. When you recombine them, you now subject them to the initial reservoir conditions, which is the pressure and temperature of the reservoir conditions. So when you subject them to those in the understand, and when we want to look at the the downhole sample is very, very expensive. That's where we use maintenance for that tool that is for that bottle that is going downhole, so that when they pick up the fluid sample from that downhole, that nitrogen will now be what will be providing the pressure for that crude oil sample, thereby maintaining that pressure to the surface. But some of the downsides of this is that it's expensive, it is time consuming, and you can't do that for a well that you can't do that at the center you are producing. No, you have to do that somewhere else. So this also to actually okay. Then another advantage of it is that it's in most cases it's cheaper because there is no form of distortion in the reservoir. You're actually picking this information directly from the reservoir. So in most cases, it gives like a higher accuracy, but we have looked at the downside as well. Then for the surface sampling, it's fairly it's cheaper, okay. The volume you are going to collect is limited. The volume you are going to collect is limited. Okay, so it's limited to the volume of the bottle you are going. Having more volume. So if you want to get more volumes as fast as well, you can. Another thing is still that you need to take note of is that downhole sampling, most times you do it once, okay, because you will do it before you start completing and doing everything. So you wouldn't collect the sample, then start producing and want to do that whole again. No, it doesn't really work that way. But for surface, you can always do this within the life of that way. As far as production is taking place, you can always go back and take your samples. Okay, so that's it about this. Then when we now move over to the quiz session now, we are now going to look at these sampling methods in detail. Okay, so this is a typical sampling method, right? Kind of sheet where we want to categorize. At this point now, I will take my pen because I might be doing some writings. Okay, please. Okay, so I might be doing some writings for us here. Yeah. So we have this table actually tries to inform us the kind of sampling techniques that we can carry out, okay, for our different field, because these are some of the things that will come out in your quiz, and we want to test your ability to know, can we carry out this kind of sampling method for this kind of fluid? Can we carry out from this kind of fluid? So we have, I think I explained, we have the black oil, we have the volatile, we have the gas condensate, we have the wet gas and dry gas, right? So we, for the black oil, it can be the phase, that's the phase of this black oil, can be undersaturated, it can be saturated. And when we say saturated and undersaturated, what do we mean? I think at this point I will want to open up. So Bio, help me to see those that are raising up their hands that can answer that. So who can actually uh, explain to us or differentiate between something being saturated and undersaturated. So I'll be taking a pause now to get answer. Then if I don't get an answer, I'll go ahead and give the answers, provide the answers, but in the quiz, that's now where I'm going to catch many persons. So Bio, I think over to you now. Okay. Yeah, I think
Please, we can't hear you again.
Okay, okay. I was actually waiting for someone. Can you hear me now?
Yeah, I can
Okay,
hear
good. I
you.
was actually waiting for someone to give a try, but because I'm using a single screen, I can't see the chat session, so I don't know whether anybody dropped anything. But notwithstanding, let me just go ahead and explain this. So when we say something is undersaturated, obviously we are just saying that that thing is in a single phase, right? So in terms of reservoir pressure, for that fluid, the reservoir pressure is actually above the bubble point. Okay, it's above the bubble point pressure. So any fluid that can be seen that is above the bubble point, whose reservoir pressure is not just reservoir pressure, okay, starting from the initial reservoir pressure down to the pressure below immediate before the bubble point, we can say that that reservoir fluid is actually in the undersaturated zone. So when you look at a representation of that fluid, you understand that it's just completely single phase. There's no gas that has been formed. But in the saturated, the pressure, the reservoir pressure, has actually attained the has reached is equal to the bubble point pressure, right? So it's saturated. So at that point downwards, we are most likely going to expect um, some kind of gases evolving from or coming out from that liquid. Okay, so that works for black oil, volatile, gas condensate, wet, and but another thing you still need to know is that when we are now talking about gas, it's going to be like a reverse because in gas, obviously gas cannot be evolving from a gas. So because gas is the active phase, right? We are now expecting a drop of oil from it. Okay, so let's go ahead and tick this box. So we have the fluid type, which is the black oil down, like the types of the fluid types, right? So you have the phases, it can be in the undersaturated and saturated. Then you have the sampling methods, which can be the surface and the buttonhole sampling methods as well. So for the black oil now, can we get is it advisable can we get do the sampling when it is surface can we do surface sampling, can we do buttonhole sampling for a black oil? The the answer is you can do both. You can do surface, you can do buttonhole sampling for both of them. You can do for both of them. And why is that so? Is that for bottle sampling, obviously you can do that, right? Because this thing is still undersaturated. For surface, if we are not able to get a good subsurface sampling like bottom hole or down hole sampling, we can equally make use of the surface. Then when it's saturated, it's not really advisable to go and be doing buttonhole sampling. Remember, in buttonhole sampling, we assume there's an assumption that who knows this oil might be undersaturated. So you want to get it because you know it is completely oil, it's completely single phase, right? Which is obviously oil. But if it's saturated, there is no need to go and be doing bottomhole sampling when you know that this reservoir is saturated. So you can go ahead and do surface. So this one is not applicable, right? Then for volatile, you can do the same for both. You can go ahead and do the same for both of them. But once it's saturated, the same thing is applicable to this. You can just only you just be only able to do for surface, so you won't be doing for bottom hole again. Why? Because it is completely saturated, right? So that's just the idea behind this. Then for gas condensates now, which is retrograde. Okay, so retrograde is that one that usually starts most times. It can start from gas, then at some point we see it as liquid. We have some liquid components dropping out from it, okay, at the surface. So that's why you can do it for undersaturated. You can go ahead and do it for both cases, right? So even though for this gas now from the this condensates now from here downwards, we are actually entering into the gaseous system, right? So, as I mentioned initially, you're not going to be thinking in the other way around. Instead of gas coming out from oil in the gaseous phase, you are looking at oil droplets coming out from the gaseous phase. So, that same thing is applicable for gas condensates, right? So, you can go ahead and do some sampling, surface and odor sampling for when it's saturated. That's the another case when it's saturated, whereby you know that it's completely gas, right? So there is still no need to expect oil to come out from it, right? So it's not applicable to go with only surface. No need for bottom sampling again. Then for wet gas and dry gas, in most cases, if you study very well, you discover that there is no need going for bottom sampling because come on, no, you're not expecting any oil. Even if there are droplets of oil, it's too negligible that you can't even want to ascertain that. As far as you have established that this thing is wet gas or dry gas based on your solution gas oil ratio value and some other parameters you have used to confirm that. So it's always advisable for you to go ahead and do the surface sampling method, and for this applicable for both of them. This applicable for both of them. This applicable for both of them. Yeah. So I will be summarizing by talking about this a little, but in our next class, when we are going to have hands-on, I will still give further explanation to this. But why I want to just touch this a little is that we'll be reading some papers. Okay, there will be a paper that will be shared after this particular slide and after this presentation. You are expected to read that paper. When you be reading that paper, you'll be coming across some PVT parameters, right? So I just want to show you this. So if you want to take a snapshot, feel free, go ahead and take a snapshot. So this is a typical PVT parameter trend with respect to pressure. And these are some of the key questions that when you go for job interviews, either for your internship or for any graduate trainee or internship programs, you will see questions around this area, right? So that's it. So you have your BO pressure. You can see how the trend is happening down to the bubble point. Okay. Then for this oil viscosity, you can have how the behaviors are happening. So are working, but I won't be doing that for this our class now. I'll just go ahead and take questions. So I'm promising us that we are going to come back to this slide, I think, in a more practical way, because for us to analyze our PVT data, we must make sure we have this. Okay, so we make sure we understand this very well because these are some of the key questions that when something is in the single phase, that's the undersaturated. What happens when we get to the bubble point? When we start going to single phase, when gas has started evolving from the oil, how will this PVT parameter be changing? And I think when we be doing that, I will be more practical in walking us through the maths behind it or the equations behind it, so that we can understand this very well and we can go ahead and So I wouldn't just explain from the formula paper that will be shared with us in the community. You're expected to read that paper effectively, understand it very well, then expect your quiz hopefully by uh, monitor it and actually understand it very well. So at this point, I'll be stopping. I'll be stopping to. I'll be stopping to take our questions. Please feel free. Then while I will still go over to the comment section and check. So Bill, over to you. Let's take some questions.
First, thank you so much for the presentation. It was wonderful. Please, if there is any question, you can ask. Thank you. Okay, Samuel, your hand is up. You can ask your question.
Good evening. Please, can you hear me?
I can hear you.
All right. Thank you, Mr. Press. So I just want to a little bit explanation on the saturated and undersaturated in terms of bubble point pressure and reservoir pressure. Thank you.
Okay, so I'll just go ahead and share my screen and explain it. Okay, so I'm going to explain it in two ways. I'm going to explain it in two ways. So let me shift this a little bit. Uh, just confirm that you can see my screen.
Yes.
Okay, so we have established, and you know that our reservoir fluid is a combination of liquid and gas, right? So when we talk about liquid, we are talking about it can either be oil or water, right? Then for the other phase is gas, right? So we know that gas usually expands when there's a pressure drop. Okay, so when we say something is undersaturated, we are actually saying that the we have a single phase, right? And we're actually trying to say that all the gases that are meant to come out from the lake are completely dissolved. They are completely dissolved in the oil. Okay, so because they are completely dissolved in the oil, we now have a single phase, which is an oil phase or a liquid phase, right? That contains the gases completely dissolved in it. And from our analysis and from studies, it happens when the the reservoir pressure, right, which is your PR, is greater than your PB. And what is this PB? PB is just that pressure at which the first bubble of gas starts coming out from your liquid, right? But that gas is coming out does not mean that it's going to become visible, right? It must still attain some conquer some critical points for it to now flow. So a typical single phase a typical single phase of our system will just be something like this, right? Whereby you are seeing oil all over. So there's no gaseous phase, right? But once the reservoir now is saturated, that's the reservoir pressure now has now the reservoir pressure has now either is equal to this bubble point or is below it. We
Yes.
can see it's saturated. So that's where we now see some kind of uh, section or portion of the reservoir having gas, right? That's what we now call the gas cap. right? So that's how we can explain it this way. So at this point now, I don't know if Mr. Hart will want to add something, or if I have answered your question, Samuel.
All right. Yes. I think it's more clear now. Thank you so much.
All right, that's great. Okay, I can't see my
Okay,
screen, like I can't see the
patient.
chat section.
So thank you.
Patient, your hand
Thank you
is.
so much. Thank you so much, Praise. Can you hear me?
Yes, sir.
Sorry, can you hear
Okay.
you?
After her question. Patience will go, please.
Okay, patient, you can ask your question.
All right. Good evening, everyone. And
Good evening, ma.
still talking about the saturated and unsaturated. It's a little bit confusing, if I'll say, because when we talk about the conventional normal thing about something being saturated, it's more like you have maybe if I would want to use an example, maybe I have water, all right, and then I dissolve salt in it. Okay. So if it is when I have the salt completely dissolved in it and I have there's no more space for me to add salt to that water. More like I start seeing crystals and I say that water is saturated with salt. Okay. And then but if it is a case where I have water and then I keep adding salt and I see the salt still getting dissolved, I could say that water is unsaturated. But this explanation seems like the reverse to me. So if I don't know if you could just help me clear it more. Thank you.
Okay, so I think Mr. Hart, you can go ahead and take that, then maybe add some additional things.
All right. Thank you. I think what Patience has done is that she has explained it to us from the basic concept. And yeah, she's absolutely correct. All right. But let's put an explanation to this that so what praise has given is correct. So our fluid in the reservoir responds to pressure and temperature. Remember, what makes our reservoir oil is because the temperature of the reservoir is below the critical point. What makes our fluid to be gas is because the reservoir temperature is above the Cricondent temp. And by the time we look at all of this, our reservoir is under pressure. Okay, it's under pressure. The fluid is subjected to pressure. So when we are talking about undersaturated and saturated reservoir, the fluid is or less than the bubble point pressure of the oil. Okay, so what Praise mentioned is correct. So when the pressure of the reservoir is less than or equal to, this is what happened. And patients, you're also correct. What happened is that gas bubbles start liberating in the reservoir, which is like the salt dissolution phenomenon. All right, we've gotten to the point where instead of salt, but conical flask or container. But in this regards, right now, in the reservoir, what we see is that because the pressure has equilibrated with that of the bubble point or has gone below the bubble point, we now see gas, which is supposed to be dissolved. We now see the gas liberating, coming out of the system. Now, it may not be visible, it may not visibly create a gas cap, all right? But it will keep accumulating, it will keep coming out of solution. So that is basically what your example was desaturated. That is the same way also in the reservoir, the gas that was already dissolved also comes out of the solution and then it starts accumulating. It can accumulate and create a visible gas cap that may become mobile or that may remain immobile. Okay. Whereas when we talk about under saturation, the reverse is the case. Then we have a scenario where the reservoir pressure, okay, is gas and keeping it within the oil such that the gas does not come out of the oil but remain within the oil, keeping the system as a single liquid phase. Okay, so that is basically what we see in both scenario. I think the same thing, but it's that in one system we are dissolving solid, in the other system we are dissolving gas. All right, so that is the difference. Yeah. Patience, I don't know if that is clear.
Yes, it is. I get it clear now. Thank you very much.